Okay, we're jumping into the last section of chapter 3, and I'm excited about this because on Thursday we get to start chapter 4, which is super fun and a very different flavor from what we've been doing. But for today, we're talking about inverse trig functions and how to take derivatives and deal with those functions. So from the past, I'm going to recall some, well, what are called the Pythagorean identities. And this really comes from imagining the unit circle. So we got the unit circle here, and y, and if you take an angle in standard position, there's angle theta. That length is 1, and the point on the circle here is the cosine of the angle comma sine of the angle, right? This is just x and y. So every ordered pair on the unit circle relates to a cosine and sine of some angle. So if you look at this, x squared plus y squared equals 1. So that says what? It says cosine squared theta plus sine squared theta equal 1. It's just this side squared plus this side squared equals 1. So there's the first Pythagorean identity. And the other two you get from doing a little bit of division. If you divide through, so if you divide through this equation by cosine squared, you get 1 plus tangent squared of theta equals secant squared theta. And that's the second identity. And these are the only two we actually use, but if you divide through by sine squared, you get cotangent squared theta plus 1 equals cosecant squared theta. You usually don't need this third one. You can get everything done with the other two, as you'll see in a second. Okay, so from last night's video that you watched for homework, just to recall what you've learned in the past, we're going to consider the function y equals the sine inverse of x, and it's implied that y lies between pi over 2 and minus pi over 2, and x lies between 1 and minus 1. And we want to compute dy dx. We want to find a derivative for the sine inverse of x function. Okay. And I love this construction. You can do this 6 times, and it works every time for all different 6 functions. So if you take the sine of both sides, you get the sine of y equals x, because sine undoes sine inverse. Right? So putting this in red, what I said was I'm going to take the sine of y, and I'm going to take the sine of the sine inverse of x, which we know from the video last night that that's just x. So now we have sine of y equals x. Okay? And what we're going to use here, one of our best tools, is implicit differentiation. So we're going to take the derivative with respect to x of both sides of the equation. Right? And this gives me cosine y times dy dx equals 1. Right? And we're looking for dy dx. So now if you divide by cosine, you get dy dx equals 1 over cosine of y. Okay. So here's where it gets exciting. If you go back up to this equation here, oops, I want the marker here, highlighter. If you solve this for cosine, you get what? You get the square root of 1 minus sine squared of y. Right? That's just solving for cosine of y. You get a plus or minus there, but it remains plus because of the way y is defined. right? Because over here, y lies between minus pi over 2 and pi over 2. And cosine's positive there, so we're looking for the positive square root here. And then from, this is the cool step, for me at least, then from this identity, you get that the sine of y is x, so this becomes 1 over the square root of 1 minus x squared, because the sine of y equals x. And there you have it. Right? The derivative of the sine inverse of x is 1 over 1 minus x squared, square rooted. Okay. So let's do an example using this found definition. Right? So we want to find the tangent line to the curve y equals sine inverse of 2x at the point x equals 1/4. Okay. So we need to use the chain rule here. So chain rule. Because the inside of this thing is 2x, right? So the derivative of that is 2. So dy dx is 1 over 1 minus the quantity 2x squared times the derivative of 2x. All right, chain rule. And that equals 2 over the square root of 1 minus 4x squared. Okay. So there's the derivative. And if we want to find m tangent, we have to evaluate this at x equals 1/4. So this is 2 over square root of 1 minus 4 times 1/16, which is 2 over 3/4, and that's 4 over root 3. So this turns out to be m tan. Okay. So we want the point on the line. So the point on the line is 1/4 y of 1/4, which is 1/4 sine inverse of 2 times a fourth, and that's the sine inverse of a half. That's the sine inverse. Oops. That's the sine inverse of a half. And let's see here. Sine is opposite over hypotenuse. So that's 1/4 pi over 6. And then so the point slope equation of the line is y minus pi 6 equals 4 over root 3 x minus 1/4. Use a purple highlighter. It's pretty dark. Okay. All right, let's do one more of these. I love this construction. Right, so if we let y equal tan inverse of x, x has all real numbers for its domain, and y lies between pi over 2 and minus, oh, come on. Pi over 2 and minus pi over 2, non-inclusive, okay? So it's the exact same as before. Take the tangent of both sides. You get tan of y equals x. Implicitly differentiate. You get secant squared y times 2y dx equals 1. So solving for dy dx, you get 1 over secant squared y. And this is equal to 1 plus tan squared. Oops. And just like before, the tan of y is x, so you get 1 over 1 plus x squared. So end result is the derivative of tan inverse of x is 1 over 1 plus x squared. Okay, well, this is the end of chapter 3, and you have enough to do the homework, which is due Friday. And I will see you in a minute to have a chat about some things and some guided practice.